Hi, traffic engineering class. In the last session, we talked about stopping sight distance on crest vertical curves. Today, we start talking about stopping sight distance on sag vertical curves. So let's take a look into this graph. Here I'm showing you a sag vertical curve. You see the length of the curve here as shown by L. You see PVC, PVI, and PVT. So what is going to be limiting your sight distance on this curve, assuming that you are a vehicle that are traveling, you are in a vehicle and you are traveling from left to right? Are you going to have any problem in daytime? Is there anything that limits your stopping sight distance? And what would be the answer to that question in nighttime? So I'm going to put this vehicle here, and in daytime there is nothing there to limit your eyesight, so you can see as long as you want on this curve. But if you are driving there during the nighttime, the headlight of your car and the angle that they have with with a horizontal plane that goes through your car, that angle is really limiting your sight distance. So assume that the headlights are at height h, and beta is the angle between the beam of light that comes from your car with the horizontal plane when your car is on a level grade. So that's beta, assume. So as we already talked about, stopping sight distance is not restricted on sag vertical curves during daytime. And so when we want to design them, we just design them for nighttime condition. So we need to make sure that we have enough headlight sight distance. And really the two important parameters there are h, the height of the headlight, and beta, or the inclined upward angle of the highlight beam relative to the horizontal plane of the car. Okay. So similar to crest vertical curves, we have two equations here, one for the assumption that stopping sight distance is less than L, the other one for the assumption that stopping sight distance is greater than L. So you can see that in these equations you still see A, you see stopping sight distance, you see H, and also we see tangent of beta, or the angle that we discussed. Again, the first equation seems to be a little bit easier than the second equation, and we can further simplify these equations by assuming values for H and beta. What do you think is a good value for H and for beta? Just think about it for a few seconds. So the design value that we use for H is 2 feet or 600 millimeters. The design value that we use for beta, or headlight angle, is 1 degree. So if you plug in these two values in the equation that I showed you on the previous slide, you will be getting two simplified equations. Those equations are shown here. L sub m would be equal to A into stopping side distance square over 400 plus 3.5 stopping side distance. This is for when stopping side distance is less than L. For the other condition, or stopping side distance greater than L, we have 2 into stopping side distance minus 400 plus 3.5 SSD over A. I have these equations in metric form just for your records, but we don't need to have them on our exams or on our homework or anything like that. Again, we go through the same process. We first assume that L is greater than stopping side distance. We calculate the minimum length of the curve based on this assumption. We compare it with stopping side distance. If it's greater than that, you're good, you're done. If it's not greater than stopping side distance, then you need to go through the second equation that assumes stopping side distance is greater than L. So similarly, we have a table here. This table has K values, stopping side distances for different design speeds, and these design speeds go from 15 to 80 miles per hour. So for each of those, stopping side distance is calculated, rate of vertical curvature, or K, is calculated, and then the design value is pretty much rounding the calculated value to the larger, to the next integer, rounding it up to the next integer. So here we have the next example, and I think it's a good place to pause for this class, and we are going to start going through this example in the next video. Hello everyone. Today I would like to continue by going through example 3.8. Just a quick reminder is that we are working on designing or finding out what has to be the minimum length of a sag vertical curve so that we can accommodate enough side distance. Now this example actually is a very good and comprehensive example, and pretty much it will recap a lot of things that we have learned so far about sag vertical curves and in general about vertical curves. So here is the example. We have an equal tangent sag vertical curve. It has an initial grade of negative 2.5. It is known that the final grade is positive. So we know that it's positive, but we don't know exactly what the value of the slope is. We also know that the low point is at elevation 270. So the low point is at elevation 270 and station 141. The PVT, point of vertical tangency, is at elevation 274 and the design speed of the curve is 35 miles per hour. Determine the station and elevation of PVC and PVI. So before looking at the solutions, I would like for you guys to pause this video for 7 or 8 minutes, go through the example, try to do it on your own, and then continue watching the video. So before going to the solution, I want to tell you this one more time, that whenever you are working on problems like this, if you start drawing them, all of a sudden the problem becomes way less complex. I'm not going to draw it here in this video, but I want you to always consider it, no matter if that's a class problem, if that's an example problem or homework problem, or in your exam, you definitely want to try drawing it. When you draw it, you look into the curves, the tangents, you look into the triangles that are there. All of a sudden a lot of things make sense. It becomes a lot easier. So first thing that we want to do here is to find the K value, the design K value for this problem. So if you remember, table 3.3 gives us K values for different design speeds. So if you go to that table, you will find out that for the design speed of 35 miles per hour, the value of K is 49. So what we did was that we selected design speed of 35. We went to table 3.3 and we found the value of 49 for K. Now, if you go back to probably the first or the second class that we had, you would remember that I introduced a hard way to find the location of the low or high point. You had to go through taking first derivative of the formulation of the parabola and going through a lot of calculations to find the location of the high or low point. Or there was an easy way that you could use K value, the initial slope of the tangent, and by multiplying those two, you could have found the location of the high or low point. So this is a sag vertical curve. So when we are talking about the location of high point or low point, we are really talking about the low point. So if you multiply K, which is 49, by 2.5, which is the initial slope, you would get a value of 122.5. So that means that the distance of the low point from PVC is 122.5 feet, or in stations it is 1 station and 22.5 feet. So if you just subtract this value from the station that is given for the low point, we can find the station of PVC. The given station for low point was 141. This was given in the problem. So we subtract 1 station and 22.5 feet. It gives you a station of 139 plus 77.5 feet for PVC. We have the elevation of the low point. It is 270 feet. We know that X is 12.20. It's 122.5. So these are known parameters to us. Also, we know that the B parameter of the parabola, if you remember, the parabola is y equal to ax squared plus bx plus c. B was one of the parameters of the parabola that is equal to G1, or negative 2.5. So we want to go forward from this point and find other parameters of the parabola. Okay, we have determined the value of B. It is equal to G1, and now we want to find the value of A. If you remember, A is equal to G2 minus G1 over 2L. Now here it's a little bit tricky because we don't have the value of L, but we know that G2 minus G1 is equal to A. And at the same time, if you remember, K was equal to L over A. As a result, L is equal to K multiplied by A. So I'm gonna substitute L in the denominator here with K in A. So I'm gonna have G2 minus G1, or A, divided by 2L, which is 2 over 2 into Ka. And what that 100 does here, what it does is that it's gonna fix the the units that we are using here. So if you have this, you see that you can cancel out A with A. 100 goes up and then we are going to have 2 into k, which is 2 over 49, 2 into 49. So you have 100 over 98, or 1.02. That's the parameter that we need to find in our parabola's equation. So we have y equal to ax squared plus bx plus c. Now the only thing that is left is finding c, and we know that at low point the elevation is given. So if I just insert y of low point, which is 270 here, and I have a 1.02, I have b, which is negative 0.25, and for x, if I put the x of low point, it's going to be 1.225. So if you just put all of these in this equation, you find out that the only unknown is c. So you just have a very simple equation to find c. C is going to be 271.53 feet. That's going to be our elevation at PVC. Now we have all the parameters here. We have a, b, c. So pretty much this parabolic equation is all known. So what we need to do here is to go and find the lengths of the curve. And to do so, now we know that the elevation at PVT is 274. So if A is known, if B is known, if C is known, if I know that the elevation at PVT is 274, if I put L, or if I find X, that's going to be the length of the curve, because from the origin to PVT, X is equal to L. You move on the horizontal plane L feet, or L stations, depending on how you have defined everything. So that's what I'm doing here. So 274 is equal to 1.02 L squared plus negative 2.5 L plus 271.53. So what you need to do is to solve this quadratic equation. It's going to give you two solutions. One is going to be not right and negative. The other one is the one that you see here, 3.2. And you see that because we have put everything in stations, or in feet per station. For the slope, the value of L is in station. So it's 3 plus 2, or 6 stations, or 320 feet. So now you can find the station of PVI. That's equal to station of PVC plus half of L. So that's just simple calculations. I have 139 plus 77.5. I add the half of the length of the curve to that. So the station of PVI is going to be 141 plus 37.8. The elevation of PVI, you just need to know the elevation of PVC and add G into L over 2 to it. Now you can see that here I put G in feet per feet, then I had to put L in feet. So that's going to be 271.53 minus 0.025 in L. That's going to be 267.52 feet. That's the elevation of PVI. Or what I could have done was to write it this way, 271.53 minus 2.5. And then if this is 2.5, it means that it is feet in stations. So now I need to write the lengths in stations. That would be 3.264 over 2, which is going to give me exact identical solution. So there are a few things left that I want to cover very quickly uh, before we finish vertical curve design. The first thing is to determine the length of the curve, not only based on stopping side distance, but also based on passing side distance. What this really means is that you want the side distance, the length of the curve be long enough to allow drivers safely pass the other driver. So they have to go into the opposing lane and then go and pass the other vehicle. If we can provide that long vertical curve lengths, then we are going to allow passing. If that's not the case, we are not going to allow passing on a vertical curve. So PSD is passing side distance. So we again have equations that we are not going to go through how we have driven them, but what you need to know is that this is for two-lane highways. So you have pretty much something like this. In one direction, the traffic goes, let's say, from west to east. In the other direction, it goes from east to west. So what one vehicle wants to do is to pass the vehicle that is in front of them. So they want to go to the other lane and then come back. And if this whole thing is happening on a vertical curve, what should be the minimum length of the curve? So again, we have the same drill. First, you need to assume that PSD is less than L. For that, we have this equation that is here, A into PSD square over 2800. If you make that assumption and then the L that you found was more than the PSD, then you're good. If not, you need to go and use this part of the equation. Now, one thing that you need to keep in mind is that for passing side distance, H1 is equal to H2, and both of them are 3.5 feet. Can someone tell me what is this point that we are referring to that is 3.5 feet? Or what do you think that point is? In other cases, it was either the height of the driver's eye or was the height of the object. So what is 3.5 feet here? So after drawing this car, that 3.5 feet is the height of the car. So that's what we are assuming here. H1 equal to H2 is the height of either a car, the height of car in either direction. Okay. So we talked about sag vertical curves, and we said that when you go through a sag vertical curve in the daytime, pretty much you don't have any restrictions, so everything is good. If you are going through that in the nighttime, the restriction is coming from the vehicle's headlight and the angle that it has with vehicle's horizontal plane. But what if you have an overpass? So if you have a vertical curve like this and you are going under something, so now this overpass that is there is going to limit our side distance. So all the equations that we have are going to change. So we want to see how this whole thing works. So we have a sag vertical curve here. You see that our initial slope is G1, our final slope is G2. Again, this is an equally tangent vertical curve, so PVI is in the middle of PVC and PVT, so that's critical. And now you have an overpass that has a distance of H sub C from the road, and this is from the low point of the road. So what is going to be our side distance? We have an equation that I'm going to go through that, but before that, let's look into these parameters. A, you know what it is. S is side distance. H1, H2 is the height of the driver's eye and the object. H sub C is new, is the clearance. You know PVC, PVT, G1, G2, and L. So the equations that we have, again, we are going to have two equations for L greater than S. You're going to go and use this equation. Then you're going to check L, and you're going to see if whether or not it is greater than S. If it is, you're good. If it is not, you have to go and use this part of the equation. So that's pretty much what I have for vertical curve design, and we are going to stop this lecture at this point. Thank you.